Everyone. Make sure you know it by, what is it, Friday? Okay. The midterm, when is it? Oh, in the 28th. Oh, yeah, next week is spectral. Next. Oh, yeah, because we've been writing the midterm. Because we have, yeah, we have to submit. So make sure you know the answer. Which I'm going to talk about. Yeah, we talked about this yesterday. You start with any basis. Yeah, any basis. And then the question is given or for normal basis. So first you find orthogonal, which just means bi j is 0. And you make it orthonormal by just dividing by the norm. Okay. And this was just one. All right. So let's do an example of this procedure. We proved this result yesterday. So let's first do R3 and then I will do polynomials. Yeah, feel free to use your mic at any moment. Please. Okay. All right, let's do it. So we start with R3. Here's a basis for R3. And the question is make it for normal. Okay. So step one, you get to pick the first one. So let's make B1 to just be the first one. It doesn't matter. You can start from anything. There's no wrong answer here. So yeah, first step is irrelevant. Now let's compute the second vector. So you take, so this is V1, this is V2, this is V3. And you set it equal to V2 and then you remove the projection of V2 from V1. So let me ask you a question. Where does this element belong? In what subspace? It belongs into some U perp. Huh? Sure, yeah. So into the span of, yeah. So, okay. Okay. So just by doing this, you made, put this together, you made B2, B1 to B0. Okay. V2, V1 are not perpendicular. Let me prove it. So you have 1 times 1 minus 1 times 0 and 1 times 1, which is 2, which is not 0. Okay? But B2, B1, 1. All right. Yeah, right. We have to compute this projection. So let's do that. So, that's all right. Let's just look at it. forget this. I forgot to put a pause. So B1, this is B1, and this is V2. And then I can divide by B1 squared. All right. So what did I do here? B1 is 1 minus 1, 1. And then I dot it with V2, which is 1, 0, 1. And I divide by the norm of B1. So basically you dot it with itself. You can just write this, you don't have to write it. So advice, don't write numbers in the test, it will take you a long time. So don't do what I'm doing. Put variables for your stuff. Trust me. Put variables for your stuff, like V1, V2, and just write the mathematics. Okay, like the symbols. You know what I mean? Yeah, then do that in your draft work. Don't because you will make mistakes if you try to like do two things at once, presentable and just make it separate. Be careful, don't make any mistakes. But use symbols. That's what I'm saying because it will be very big. Yeah. Well, I don't know how many questions there are. It's just it was a nightmare for me. So use symbols. It will be unreadable, and you might not have enough space. All right. So anyway, so when you compute this, the top becomes 1, or becomes as 2, and the bottom guy is 3 because it's 1 squared, minus 1 squared. 1 squared. So you get 2/3. That's how you get 2/3. Okay. So that's how you do the projection for B2. All right, let's go. And then you have to also do it for B3, which is, now you have to remove the previous 2. So let me ask you again. This is in what, let me call it, what is U2? Oh, a span of what? Yeah, you can, yeah, right. Yeah, so, yeah, we proved that, you're right. So, well, okay, this is what I wanted. It doesn't matter though, it's the same thing. Which is actually very interesting. You always preserve the span. Yeah, but yes. All right, so you have that B3 is perpendicular to both. So you're done there, but we have to compute it nonetheless. So, I guess up to here you can write it in whatever you do, but then don't do all the middle steps. All right. Just give the final answer. So yeah, if you have a question here, something complicated, I just took dot products and added the vectors. Okay. 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 Zoom people, if you have a question, you can put it in the chat if you want. It's fine. I'll check. Yeah, these are orthogonal, but we want orthonormal. And I did the computation. I divided by their norm. So this guy here is B3 divided by B3 squared. Okay? So that's the final answer, not just orthogonal. They want orthonormal, which is a nightmare. All right. Good. Something closer to your homework 4. let's look at it. So this is in Axler. I don't know. Anyway, so this is in Axler if you want to learn more about this inner product, because Damiano only has an exercise on it, exercise 10. But if you want to learn more about this inner product called the L2 inner product, go to Axler in the inner product, I think chapter 6. And this is an inner product on polynomials. So let me remind you why at least you get positive definite. Linearity, I think, is clear, right, from calculus. Okay, so let's look at this guy. You said, so no negative is clear, but this is tricky, right? But yeah. Anyway, so right, I remember. So this one we had the. Oh yeah, yeah. This is true. Yeah, yeah. That's right. That's right. So I thought I had an argument with the coefficients. No, anyways, no. This I'm just going to Gram-Smith, but anyways, go to Axler if you want to see at least a heuristic argument on why this is true. The formal argument goes through continuity. So let me talk about a little bit. So by contrast, because you will see it in so many places, so I want to make sure that you understand. Yeah. So by assume that without loss of generality, this guy is strictly positive for some x naught in 0, 1. And you can just isolate, right? So you have your 0 x naught minus delta, x naught minus delta, x naught plus delta. And then the rest, what is it? X naught plus delta 1 square equal to 0. This is a sum of positive numbers. So this is also 0. And hand wave, you divide by delta, you take a kind of limit, and this is about px naught squared, which you assume is strictly positive. Yeah, that's right. Yeah. Okay. All right. Find yeah. So for the standard basis, find orthogonal. I think I say here why it's okay. Let me tell you why this is not orthogonal. It looks orthogonal, right? So you might think that 1x is 0, but it's not. For this inner product, this is 0, 1 times x dx, which is what? Yeah, 1/2, which is not 0. So you do not have orthogonality, so we want to make it orthogonal, all right? And by the way, just to remind you, there's another inner product given by the coordinate map. And this is a summation of pk, qk, and here they are orthogonal. So let me call this 2. So 1x in 2 is equal to 1 times 0 plus 0 times 1, which is 0. Yeah, it's cool, eh? No. They're the same vector space, but different inner product space. You measure differently, like you have feet and meters, different like measuring sticks. And they're not even I mean, yeah, go ahead, yes. That's right, yeah. Yeah, well, no, all of them are because you can, yeah, exactly. But, yeah, no, so, I mean, it's just how you measure things. So here we use a different measurement step. All right, so orthogonality. First step doesn't matter, just pick one. So B1 is 1. And then to find the B2, you will remove the projection. So again, this is in the U perp, where U is the span of 1. Okay. So that means that B2, 1 is indeed 0. This is what you want. So let's find this. So you just have to compute these inner products. So 1 with x, and then the norm of 1. So like we just said before, this guy is a half. Okay, I have the answer. So yeah, the top is a half, and the thing we divide by is actually 1. Okay. So that's your guy. So let's check it. We're saying B2, 1 is 0. So why is that? So this is 1, and then x minus a half, right? Which is exactly what we want. Okay. So we got our orthogonality for B2. B3, you have to remove 2 integrals. So now this guy is in U2 perp, where U2 is the span of 1 and x minus a half. Everybody happy? All right. We have to compute this. So I know it's starting to look terrible. This one this one, no, we didn't get it because it's x squared. So what is the integral of x squared? First year complex. Oh, wait, I want to see. Yes. Huh? Yeah, but what's the number when you integrate 0? Yeah, 1 over. Okay, so all right. Do I have my numbers? Yeah. So I think that's a typo. Yeah, this is a typo. So yeah, minus 1/3. Yeah, yeah. So this is minus 1/3 1, and then you can also compute these two integrals, and you get 1/12, 1/12. Okay. So it's starting to look terrible, right? So CB, our basis would be 1, x minus a half, and then x squared minus 1/3. Why I have it? It's more beautiful. Yeah, so it would be 1, x minus a half, and x squared minus x minus a third. This guy is orthogonal with respect to the PQ integral. Okay. All right. Let's go. If you have a question, just tell me. No? All right. So I don't know how many weeks we have till April 4, something like that. 3. Yeah, we can prove the following 3 theorems. So do I have it here? I'll talk about it here. So yeah, this week will be next week a spectral theorem. So you give me some maps called normal, then we can diagonalize its representation. So that will be one of the big theorems here. And it turns out that we're almost there. So even though you don't have diagonal, if you look at over the complex numbers, not the reals, I will give you a counter example, you're almost there. So start with a V complex dimensional vector space and give me any linear map. I mean, any map. It doesn't matter. Anything. Then there is a basis where you can write it in upper triangular form. So I didn't use any words like diagonalizable, multiplicity, geometric multiplicity. It doesn't matter. You always have this. Okay, so you always have this. All right, and this will be the basis for spectral theorem and Jordan form stuff. But this is the starting point. But first, you can, just to remind you some words, bring into low echelon. So, in other words, all we're doing is Gaussian elimination. That's it. Nothing else. All right. So, yeah. So for if your underlying field are the reals, this theorem is false. And take any matrix that has non-real eigenvalues, okay? Then you cannot transform it to an upper triangular matrix. And here's the example. So you take this rotation matrix you saw in first week. There is no P that can take you to upper triangular. And I think I asked why. I want to see if you can figure it out. So why is that? Why are we not able to do this? Class people, Zoom people, all people. What's the contradiction? If you had this to be true, what would be the wait, I want people to think about it. You have the argument? Yeah. So let's see how to write this. We proved a couple of weeks ago that if A is similar to B, so you have this, then when you compute the characteristic polynomial, A minus lambda I, they actually have the same characteristic polynomial. Okay. I can repeat, I mean, the proof wasn't hard to basically write it like this. And then you do the same, right? So P inverse, and then you can do this trick with lambda over here because they're the identity. But this is just lambda, so you can bring it out like this. Okay, and then you use the determinant as multiplicative. So this guy would be determinant of P, characteristic polynomial of this guy times determinant of P inverse but then determinant of P characteristic, and this is 1 over determinant of P, so they cancel out. So, all right, so that means they have the same eigenvalues, and exactly, every upper triangular matrix, so if B was AB0C, then, you know, the eigenvalues would just be A and C, just the diagonal entries. Okay? I mean, you can do this by force, you just compute the characteristic and you find the roots. So you can do this if you. Let's do it. So determinant of B minus lambda I. This is determinant of A minus lambda 0, C minus lambda B, which is A minus lambda, C minus lambda. So the roots of the characteristic are lambda equal to AC. Okay? Okay. So exactly as he said, the problem is this guy has complex eigenvalues and this guy has real eigenvalues. The moment we say the field are the reals, we are implying that A, B, C are real numbers, right? And we discussed that the eigenvalues will be AC, but here they were, I think it was like plus minus I, something. So, can't even do it in my head. I can, so. Yeah, let me do it. So it was minus lambda 1 minus 1 minus lambda. You take determinant of this, and you get lambda squared plus 1, right? And you want this to be 0, so you get lambda equal to plus minus I. Okay? So that's the problem. The moment you force your matrix centers to be real, you force the eigenvalues to be real, but these eigenvalues are not real. Okay. All right. Good. So I hope I drove it in that you have to work over complex numbers. You miss a lot of information when you work over the reals. That's the lesson here. Complex numbers are very nice in that way. I hope more people use it. They do. All right, expected theorem. Next week we're going to prove this for T normal maps. The next 2 weeks we're going to extend the result we just talked about. Namely, any linear map can be written in the following form. So it will be upper triangular, but with a little bit of stuff above the diagonal, and then zeros. So the Jordan form says that you're mostly 0. Okay? For any map. This is not normal map, symmetric map, self-adjoint map, any linear map over the complex numbers. So that's the main result before we finish. Okay. Can you remind me what operation we had for turning matrices into upper triangular? What did we learn? What tricks did you learn in the trade? Right. So let's do an example to. So we start with this matrix, and we're gonna write it in upper triangular form. For 2 by 2, the characteristic formula is nice. So you just take trace and determinant. So this guy over here is lambda squared minus 2 lambda plus 1, which is this. Okay. So the roots are 1 with multiplicity 2, right? Okay. And then let's find the eigenvector. So we have this matrix and we remove -1, -1. And can anybody guess what's the solution? What A, B solve this? Yeah, so what do you have? You have the system of, yeah, minus A, B is 0, and A plus B is 0. So you get the infinite solutions, A minus B. So you can just pick, you have a free variable. So your V is of the form A minus A, so 1 minus 1. Okay? So the solution here is the vectors of this form. Right, so is this matrix diagonalizable? Why not? What result do we have that gives this? Right, and so what's the geometric here? Yeah, we found all of them. So we found all the eigenvectors. So E of 1 is the span of 1 minus 1, whose dimension is 1, right? But the algebraic multiplicity is 2, and they're not equal. So M is not diagonalizable. That means you cannot write M as P 1, 1, 0, 0. In theory, I mean, using the, okay, we'll talk about this later, but it's not diagonalizable. So we'll come back to this. You cannot use the machinery. However, you have an upper matrix triangular representation. And I should put a star here. So this is star. So we can prove a result, right? That theorem we talked about, that you can always find a basis B so that you can represent your matrix M in upper triangular form, where you put the eigenvalues on the diagonal. But in other words, you can write M in that form. Okay. And actually, you do know what P is. So let me, yeah, any guess what matrix P will be? So we want to go from here to here. This is a little bit of a review. You don't have to give me the matrix, just tell me like, yeah, you know? Do you understand that? Anybody? 1 minus 1? Oh. Please use the mic. Yeah, please use the mic when you, or I have to check the chat. Right, so let's see. You use the elementary row operations. Let's look at it. All right. Yeah, so remember, whenever you want to do elementary row operations, so let's say you have this guy and you want to switch rows. So that's the first step. You can get this by multiplying by this matrix. So 0, 1, 0, 1, 0. What is that? 0 minus 1, 1, 2. If you do the multiplication, you get the switching of rows. Have you seen this before? But they never gave you the matrix? Oh, okay, okay. They gave you, did they give you the matrix? Okay, yeah, perfect, all right. So this guy switches rows. And this guy multiplies by -1. The second row, yeah. Because we want to turn this into 1, 1, 0, 2. Okay? Because we want to have the eigenvalue. We want to have, because the eigenvalue is 1. Does that make any sense? Oh, okay, yeah, yeah. I knew I'd, no, I have to, I did it right. Then I corrected it, but I corrected it wrong. That's right, that's right. I have to, I'm so sorry. I will fix it later. So this is P in, no, it's not P inverse. Okay, so I will fix it, but this will be switched. So yeah, first you have to switch rows, and then you have to multiply by that. Okay. Yeah. So you flip it, and then you can do it either way. Well, actually, either way it works. I'm sorry. Elementary operation is a commutative operation. That works as well, I think. No, it doesn't. I know how to fix it. Put a -1 over here. Okay, that's easy. All right. Yes. Yeah, yeah. It doesn't matter which way you. Yeah, it doesn't matter. As long as you define what P is, it's okay. All right. Questions? Well, I just did this because you see all these abstract theorems, and they say there exists, this exists, that exists. But how do you do it in practice when you want to sit down in your new job at Wall Street? You will need to know. We'll need to know how to do this stuff. So if you want like a keyword, this is called LU decomposition. Okay. And it's basically this row matrix operations. Understand? Okay. And there's also another one, just to give you another one, it's called Schur decomposition. So people have been developing a lot of things to find these P matrices. There's many ways to do it, depending on your needs. Because this elementary row operation is not good computation. You have to, like, as your matrices grow, you have to do more switching and moving. And so there's other ways to get the same upper triangular form faster. Okay, good. Let's prove this result in abstract, and then, yeah, so we're going to prove the abstract result today and Monday, Tuesday. We prove this by induction. So the result was that, where is it? That you give me any linear map, I can find you a basis so that its representation will be upper triangle. That's the result. We're going to prove today and Tuesday. Okay. All right. All right. So let's go. We'll prove this by induction. So over the dimension of the space, over a dimension of V. So when the dimension of V is 1, why is it immediate that the TB is upper triangular? Just to understand that. Yeah, okay, go ahead. Yeah, it's a single element. So this guy is upper triangular. It's one guy. So base case is obvious, which is great. So we assume that if you give me any subspace, whose dimension is strictly less than n, then my assumption is that I have upper triangular representation. Do I have it here? Okay, yeah. So, yeah, anyway, so that's the assumption that when you restrict T to U, there exists some basis, call it, I don't know, B tilde, such that this is upper triangular. Do you understand? And B tilde is a basis for, so span of B tilde is U. So that's our inductive hypothesis. And I have to go to K plus 1. So I have it for all numbers less than n, strictly less than n. I have to go to n. Okay. That's called the strong induction, because you're not just assuming. Anyways, so this is basically like strong induction, because you're going through all, you're using all your information, not just n minus 1. Yeah, so this is called strong induction. All right, let's go. So I'm going to build an explicit U and explicit basis. Yeah, but first, upper triangular. What does that even mean in our world? So we have to come back to linear maps, because we're proving it for all linear maps. So we have to come back there. We cannot just work with matrices anymore, because it's too cumbersome. I have to keep moving with coordinate maps. So you have to come back to linear maps. And this is the equivalent statement of upper triangular. Okay. So what does it say? It says that if you give me any vector, let's say 2u1, then tu1 is in the span of u1. Okay, so you put something and then you put 0. Second guy, tu2 is in the span of u1, u2. You put stuff and then 0. This matrix is the TB, where this is B. Do you understand? B to B. Is that okay? TU3, it's the span of U1, U2, U3, star, 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 and then zeros. So if you keep doing this, you're going to get upper triangular. So if you want to check something is upper triangular, it suffices to prove this span statement. So equivalent. Okay. That's the main point of this whole proof, that we can do this, and then the other stuff is like. So make sure if you have a question here, otherwise you will get lost there. Okay, all right. Right, we're gonna build U. So, and from there we can extend to V. So let's start from there. Every linear map has at least one eigenvalue in complex numbers. Why is that true? Why do you all? Yes. Right. So you for which polynomial? So you have yeah. So t minus lambda I. This is equal to any representation. So it's invariant under any representation. Okay. And then this is a polynomial, P lambda, lambda in C, and fundamental theorem says that there's always a solution. It's amazing how much machinery you need to prove this that you haven't seen in first year or second. Like, there's no simple proof for this. But yeah, this is fundamental theorem. So fundamental theorem of algebra. Every polynomial has a complex root. And if you want to get n roots, you just use Euclidean division. But the amazingly hard result is showing the existence of one root. That's hard. It's amazingly hard just to get one root. The other, you just do Euclidean division. Because you get another polynomial and then you get another, but you apply it again. You get, like by Euclidean division, you get a new polynomial which has a root. So then you divide again, you have another polynomial. Yeah. Right. Then you apply the theorem again and all right. So this lambda exists, so we can work with this U. So what is this U? You take the image of this map, T minus lambda I, right? That goes from V to V. This map is interesting. Why is it interesting? What do we know about T minus lambda I kernel? What do we know about the kernel of this? What is it? Huh? No, but we know something specific. What is that? It's A lambda. Right? What? So, right? Because T minus lambda I V equal to 0 is the same as TV equal to lambda V. So, so hopefully things started to spin. You have an image, you have a kernel. What's the theorem we like? Huh? Yeah, right. Yeah. So the rank nullity dimension theorem. Yes. So that's how we're gonna use this stuff here. All right. Let's see. So we have to prove that this dimension is strictly less than V so that we can apply our induction. Our induction hypothesis. Is that okay so far, Zoom people? If you have a question, you can use the chat, it's fine. I will check. I feel bad, you guys are all alone there. You can ask questions. So to apply our inductive hypothesis, I have to show that dim U is strictly less than dim V. Okay, I need this. This is my induction. If they're equal, then I cannot use it. All right. So question 1, T minus lambda I is not injective. Why is that the case? Right, E lambda is non-trivial. So we prove that P lambda has a root, lambda. But what is that? This is determinant of T minus lambda I. So what do I want to say? Right, yeah, has a root lambda star. So this guy is 0. Okay. I mean, I should put lambda star here just to make it clear. So this guy is 0. What have you learned about this and invertibility? Yeah, it's not invertible. Let me do all the steps. And then what did we prove about this in terms of injectivity? Yeah, exactly, perfect. So, but I will explain what he said. So let me not. So indeed, this is not injective. So let's see why that is. Let me remind you. So, so invertible is the same as bijective. Okay. So this is basically the definition. So there's not much here. But we prove that when V goes from, when a map S goes from V to V, then you have rank nullity. So dimension of kernel of S, let me put absolute values. Is equal to V. To be bijective, it means that image of S is the whole space, V, right? So from here, you get that the kernel of S is 0. Okay, let me find this. So, in other words, when S goes from V to V, invertible is the same as the kernel of S being 0, which we defined as being injective. Okay, you don't have to write any of this in your test or whatever. We proved this from class. I learned this. Done. Don't kill yourself with rationality. Okay, so you can reference all this stuff from class, even if it's not in the book precisely. I did it, so you can use it. All right. So it's not injective because the determinant is 0. So this map is not invertible. So because it's not, oh, it's not, okay. We'll continue on Tuesday. Okay, thank you. Thank you. Yeah, I have a good question. Okay, bye. Yeah, I remember, yeah.